So in this video, we're going to discuss subspaces of Rn, and in particular, the subspaces associated with a matrix. So the column space, the row space, and the null space. And from there, we'll then discuss what it means to have a basis for a subspace. So why do we do it? Well, it basically introduces the most important ideas of the course all at once, and it allows us to lean on our geometric intuition on a world where we can see it and be able to use algebra to extend those ideas into places where you just can't. But we need some kind of object that fits in both worlds. That's the subspace. Now, the span of vectors is just a generalization of lines and planes. Remember those formulas? So you can think of subspaces as a way to generalize the span of vectors. So we call a collection of vectors, S, from Rn, a subspace of Rn if it has three properties. The first one is it's not empty. Usually we just insist that the zero vector's in it, but it's essentially there's something inside of it. The second thing is if any vector's in the set and you take any real number, then the scalar multiple of that particular vector is also in the space. And finally, if you take two vectors in the space and you add them, it's also in the space. Notice that these two by itself essentially just say that if you give me any set of vectors and any set of scalars and form any linear combination of them, that object is still in the space. So, subspaces are just a way of saying this is a set that's closed under linear combinations, all potential linear combinations of all the objects inside of it. Now recall that currently spans require a finite number of vectors to define the set of linear combinations. Subspaces is just a way to get around that because we don't bother saying what's in it. We just say it just is closed under addition and it's closed under scalar multiplication. So what we need then is some kind of basic object that we know is a subspace. Now, if a span of a set of vectors is in fact supposed to be a subspace, we really should prove that. So let's just do it quickly. Let's suppose you have a bunch of vectors. Notice this finite set of vectors in Rn. Then the span of those k vectors is a subspace in Rn. All I have to do is to check the three properties. So let S be that span. Now, since if you take a linear combination of these vectors where all the scalars are zero, that vector is in S by definition, right? Because it's the set of all linear combinations of those vectors. But that linear combination equals the zero vector. So the zero vector is in the set automatically. The next is a little more complicated, but it's not that bad. Let's just take two vectors that are in S. If it's in S, it's a linear combination of the vectors v1 through vk. And let's just add them. But if you add them, we still have all those 8 properties that give us the algebraic properties for addition of vectors and scalar multiplication. Because of that, you can kind of just like recollect everything, and you could see that the sum is a linear combination of v1 up to vk. It's just the scalars are c1 plus d1 and so on. You can actually do the exact same thing with scalar multiplication. Because if you take any scalar and multiply it to the vector u, you just multiply the scalar all the way through. So you then have a linear combination of the vectors v1 through vk. So S, the span of these vectors v1 through vk, is already a subspace. It's a particular case of it. Let's now go over 2 examples of sets that are subspaces and 2 examples that are not. So first, consider a set of vectors whose components are x, y, z in R3 so that x is the free variable, y is then 4x, and z is negative 3x. If you let R be one of these vectors in this set, it can be written as x, y, z, but just replace y with 4x and z with negative 3x. Notice you can then take the x out. So the vector R is just some multiple of 1, 4, 3. And as the vector is a multiple of 1, 4, 3, that's the equation of a line. It's just that it's not written the normal way. Normally the parameter is t or s, and we call the vector x, but that's exactly the equation of a line. Since it then corresponds, every single one of these vectors in this particular set is a multiple of 1, 4, 3, the set then is therefore just the span of that vector. As the set is a span of one vector, it's a spanning set, and therefore, or it's just a span, and therefore it is a subspace. Pretty easy. Let's just try it again. So once again, let's take a vector in R3, components are x, y, z, and let's say y is 4x plus 3z. Doing the same kind of thing, I'll now show that this is a span of some vectors, and therefore must be a subspace. So let R be one of these vectors. Notice that that can be written as x, y, z, but y is replaced with 4x plus 3z. But then you could rip that apart, so it's a multiple of one vector plus a multiple z times another vector. And if you think about it, that's the equation of a plane. It's just the parameters are called x and z, and the name of the vector is called r instead of x. That's actually the vector form of a plane. But more importantly, though, this shows you that every single vector in this set is a linear combination of these two vectors. Therefore, the set is spanned by those two vectors. It's a span of a bunch of vectors. As it's a span, it must be a subspace from what I just showed you. Now let's look at some examples where they're not a subspace. If it's not a subspace, what you're looking for is something that violates one of the three properties. This is called a counterexample. You're trying to show that, for example, that it's empty, or the zero vector is not in it, or that the sum of two vectors is not in it, or a multiple of one of its vectors is not back in that space. So as a good example here, let's look at the set of all vectors in R3 where y is equal to 4x plus 1. The plus 1 is what screws things up. So notice that every single vector in this space is of the form x comma 4x plus 1 comma z for some real x and z. But that means instantly then the zero vector can't be in this space. Because if the zero vector is in there, that means then x would have to equal 0, and at the same time 4x plus 1 would have to equal 0, and that you can't have that at the same time. So the zero vector cannot be represented this way, and therefore, since the zero vector is not in the space, this is not a subspace of R3. Okay, let's try it again. Now, as a quick result then, from now on, if the set can't contain the zero vector, it's instantly a subspace. It's something to remember. But you can also use it other ways too, but usually the zero vector is the one you want to pick on. This time, let's look at the set of vectors x, y in R2, where x times y is just not negative. It's non-negative. So that actually is also not a subspace. But notice the zero vector is in the space this time. 0, 0, those components, if you multiply them, that is greater than or equal to 0. So the vector 0, 0 is in the space. So I have to now check the other two ones, the other two things. A good one here would then be is to take two vectors that are in the space, add them, and convince me that it's not. That's the sum is not in it. You just have to fish around for good examples. So in this case, if you take the vectors -2, -4, notice that product is positive, and take the vector 3, 3, notice that product is positive. Those two vectors are definitely in this set, by just definition. But when you add them, you get the vector -1, 1. But that's not in the set, because the product of those entries is -1. It's negative. So you can find two vectors in this set whose sum is not in the set. The set is not closed under linear combinations. So it's just not a subspace of R2. So let's now go and look at the subspaces that are naturally associated with the matrix. So there are 4 such subspaces. I'm going to look at only 2 for now. One is called the row space of a matrix. That is just the subspace that is spanned by the rows. And then there's the column space, which is the subspace that is spanned by the column. So they're not really questions if it's a subspace or not. But what you might wonder is, how do I know when a vector is in, say, the column space or the row space? So there's one fairly straightforward way to go do so. It goes like this. If you have a vector that's in the column space, that can only happen if a times x equals b is consistent. The reason is it's a direct consequence of a theorem we've already seen, 2.4. So I'll quickly prove it. By definition, a vector B is in the column space if and only if B is a linear combination of the columns of A. But by our best friend, theorem 2.4 from section 2.3, this just states it's equivalent to saying that A times X equals B is a consistent system. So, as an example, I want to know, given this matrix A, is this vector in the column space of A? So that's easily done by just going and creating the augmented matrix for the corresponding system of AX equals this vector and row reducing it. Notice when you row reduce it, the corresponding system is consistent because there's no leading entry in the last column. So yeah, the answer is yeah, this vector is in the column space. So you could do the same sort of thing if you wanted to try to determine if a row vector is in a row space. The trick is here is to notice that's equivalent to saying is B transpose in the column space of A transpose. So if you want to answer that question, instead, you just look at the corresponding augmented matrix and row reduce it and notice that the system is consistent. In this case, there's no leading entry in the very last column, so the system is consistent. In fact, the corresponding system this time has an infinite number of solutions, but we don't care how many solutions there are. We don't care how many ways or different possible linear combinations there are of the rows or of these columns that would give you this vector. Or in the case of the original statement, we don't care how many linear combinations of the rows of A will give you the vector B. It's just that there is one. That's the only thing that actually matters. So I've now given you a technique that will determine whether a vector is in the column space by determining if a certain corresponding system is consistent. And because of that, by using transposes, we actually can also go and determine whether a vector is in the row space of matrix. But I don't want to use transposes if I don't have to. So instead, let's attack the problem again. I want to know, is this vector 3, 4 isn't in the row space of the matrix A? So this time, when we form the augmented matrix, I want you to augment it by adding on a row instead of a column. Like so. Go ahead and use row operations like always, but never actually swap out the last row. So as I go through that process to get a row echelon form, notice that the last row is zeros. Now start there, row of zeros, and work backwards, like we did before in a previous example. By using these row operations, you can then see that the fourth row of the original matrix is actually a linear combination of the rows above it, which means that 3, 4, that's in the row space of A, because it's a linear combination of the rows of A. Neat, right? Now you may wonder then, why did I insist on not swapping? Let's talk about that. So, as a theorem, a vector W is in the row space of a matrix A if and only if when you take A and augment it with W on the bottom, if you can row reduce it to a new matrix where the bottom row is 0 and you never swapped out the last row. So why? So just first remember that whenever you take row operations on a matrix, all you're actually doing is forming linear combinations of the rows of the matrix. That's all you're ever doing. So that means then the rows of this final augmented matrix as a 0 on the bottom is already known to all those rows are linear combinations of the rows of the first matrix with A on top and W at the bottom. Well, but that means then W though is in the row space if and only if that it's a linear combination of the rows of A, right? That's just the definition of what it means to be in the row space of A. But that means then, if that's true, since I'm using only row operations that allow me to go and take a multiple of a row above the last row and add it to the last row, that's the only way to introduce a row of zeros, because I can't multiply the last row by 0 and I can't swap in a row of zeros. So that means then that there must have been row operations on the rows of A that I take multiples of them and add to the last row in order to get the row of zeros. Therefore, W then has to be a linear combination of the rows of A. Now, because of that, you can then use that exact same technique if you want to answer a question about a column space. It's just that we really often don't. So if you want to know whether this particular vector is in the column space of A, one way to do that is to notice that's equivalent to saying, is this row vector in the row space of A transpose? So then you can kind of augment A transpose and put B transpose at the bottom, and then I can row reduce it. When I row reduce it, just don't ever swap out the last row. Notice that the last row, it's impossible to make that last row be 0. The reason is because it has a leading entry in it, and there's no way to swap out of it. You can't swap that leading entry out of that row. So because of that, it can never be 0. And that means then this vector B actually is not. B transpose is not in the row space of A transpose, which means B is not in the column space of A. Now let's take a small detour. We know that there's a way for us to determine whether a vector is in the column space of a matrix through augmenting the matrix with a column being the vector, and then just doing row reduction. We could also, though, determine whether a vector is in the row space by, once again, taking the matrix and just adding on that vector as a row at the very end, and then doing row reduction. I'd like to know then, is it possible that if I don't do the adding on the row, if I just do row operations on a matrix to get a row equivalent matrix, would the row space of the original matrix be the same as the row space of the new matrix? Would the column space of the original matrix be equal to the column space of the new matrix? And one of these is yes, and one of those is no. The reason is, to go through the argument, we need to know a little bit more about spanning sets. Besides, these results will be useful for later on. So, just as an important fact about spanning sets, suppose you have a set of vectors U, and they're all linear combinations of vectors you find in a set V. Then the span of U is instantly contained in the span of V. You think of it as the V is the parents, they define the boundaries of their neighborhood. Their children are the linear combinations, and they can't get out of the neighborhood. They can't possibly become larger than their defined neighborhood. So to see kind of why, it's just a matter of just being careful with the notation. So suppose that U is in the span of the vectors in the set U. I'm going to show you that this vector U is actually in the span of V. So if that's true, then U is a linear combination of U1, U2 up to UM. But I know that U1 up to UM, they're all linear combinations of the vectors in V, because that's one of the assumptions. So U1 can be written as a linear combination of vectors in V. U2 can be written as a linear combination of the vectors in V, and so on. All I want you to do is find out what those linear combinations are and simply replace in equation 1, U1, U2 up to UM with what they're equal to. And then just add like terms. Once you do that, you'll see that the vector U has to be a linear combination of the vectors you find in V. That means then, by definition, that U is in the span of V. So if U is in the span of V, that means then that every single vector in the span of U is automatically in the span of V. So the span of U is contained in the span of V. Nice, right? Simple. But we have a nice, really nice consequence from that is what if all the vectors in U are linear combinations of the vectors you find in V, and vice versa. So that means all the vectors in V are linear combinations of the vectors you find in the set U. Then the span of U actually has to equal the span of V. You just use that theorem twice to show that one contains the other and vice versa. If they contain each other, that means they have to be equal. Now that then leads to this really nice theorem, and that is, what if you know already that one vector is a linear combination of a bunch of others? And then you want to know the span of those vectors. Then you can take the vector that was the linear combination of the others and remove it, and the span doesn't change. So if one vector is a linear combination of other vectors and you remove it from the set and find the span of what's left over, that has to be actually the same space. The same space, because of the previous theorem. Also, as a direct consequence of that one, if the 0 vector is among the vectors that are forming the span, The 0 vector is always a linear combination of everything else. So then you can throw that vector away, the 0 vector away, and the span doesn't change. But then, because of that, again, as another great consequence, if you have two vectors, if you have two matrices that are row equivalent, then their row spaces are always equal. That's really great, because then if we row reduce one matrix, we can row reduce the matrix to some nice form, like row echelon form, or even better, reduced row echelon form, and the row spaces of the resulting matrices are always equal. And if there's any rows of zeros, we can just kick them away because they won't add anything. So, to show why this is true, notice that if you take a matrix A, if it's row equivalent to B, there has to be a sequence of row operations that do it. So there's a bunch of row operations that go from A to B. But that means then that the rows of B are linear combinations of rows of A. So by our consequence, that means then the row space of A is contained within the row space of B. But if there's row operations to transform A to B, there's row operations to go from B to A, and you can then just repeat the argument all over again. And that means then that the row space of B is contained within row space of A. So they're contained within each other. They have to be equal. Now, as a quick result, a quick way to use that, take this matrix. I want to find two vectors that span the row space. Notice there's three vectors. So which ones do we pick? That's easy. All you do is take the matrix, and we find its row echelon form, or even better, reduced row if you won't go that far. We only actually need row echelon form. But here, I'll go to reduced row. Notice that the rows of the first matrix span the space spanned by A, but the rows of the resulting matrix also span the same row space. So the row space of A is spanned by the vectors you see on the right-hand side. But the three vectors, among them, only two of them are not 0. The 0 vector we can kick away. So the row space of A is spanned by these two vectors. And you know those vectors as I and j. So then the row space of A actually equals R of R2. It's actually the pole plane. Neat, right? Sadly, though, row operations completely change the column space. So if you take a matrix like 1, 2, you can row reduce it to 1, 0. But the column space of 1, 2, all the linear combinations of 1, 2, that's a line whose slope is 2. And that's not the same as the column space of 1, 0. The column space of 1, 0 is a line, but that happens to be that'd be the x-axis. That'd be the x-axis. And those two lines are certainly not the same. So if you row reduce a matrix, it does not change the row space, but it usually completely drastically changes the column space. Okay, now that we have the column space and the row space under our belts, let's now discuss the third space, which is called the null space. So the null space is just the third fundamental subspace associated with a matrix. It's defined to be the set of all vectors so that you take A times X, you get the 0 vector. It sort of nulls out the vector. So the last fundamental space is the null space of the transpose of A. And while the row space of A is essentially the same as saying the column space of A transpose, that's not the same with null spaces. So the null space of A is not the null space of A transpose. And in fact, the four spaces are usually not in any way equal. The row space, the column space, the null space of A, and the null space of A transpose are different things. So your first question then would be well, how do I know if something's in or not? So it isn't just by definition. A vector is in the null space. If you take the matrix and you multiply the matrix to the vector on the left, you get the 0 vector. So I can easily test to see if this vector B is in the null space of A by just multiplying it out. And the answer is yes, because it's a 0 vector. So B is in the null space of this matrix. Your next question would then be well, what is the null space? So you might notice that the row space and the column space were spans of vectors. So the null space actually is also. We just have to figure out why or how. It's just a matter of solving a system because we want to know all vectors so that A times X is 0. The solution set is the null space. So we know how to solve systems. We just take the matrix, augment it as on the right with a column vector of zeros. We then row reduce it. From here, then you go back and put it in terms of the original system. We'll say the system is x, y, z. The vector then x has components of x, y, z. You can then write that in terms of the free variable. You can then take that vector and pull out the free variable, the parameter, and notice that vector x then is multiples of the vector -3, 4, 1. So that means then that the null space is then spanned by one vector. It's spanned by the vector -3, 4, 1. So the null space is that span. Easy. It's something we've been doing all this time. If you want to know a way to describe the span if you want to describe the null space of a transpose, it's the exact same process. Just take the transpose of the matrix first and then solve that corresponding system. Okay, so I've now finished defining the subspaces and the 4 fundamental subspaces of the row space of a matrix, the column space of a matrix, the null space of the matrix, and the null space of the matrix transpose. So the next video will then be just for basis.